executes the query, and all the optimization features within NIQL, as well as some of the power features within the query language and how you can use it. Let's see how fast we can breeze through within the next 40 minutes. But the good news is we have a break following this talk, so I'll be around if you have questions following this. Like I said, I'll give a quick overview to set the context for the people who have walked in, and then get into the query architecture itself, followed by the power features. Okay, so you have seen this slide from Jihan. In Couchbase 4.0, we have, in addition to the data service, we have the index service as well as the query service within the cluster. And the, hold on a moment, let me just expand this. Okay. The beauty of this is the same binary with the same installation procedure, you install all the different services in each of the node. In each node, you can choose to have just one of the services or more than one service in a single node, but it's the same installation procedure. And if you saw the keynote earlier, it's a 3-click procedure to add a new node or a new service into the cluster. So this is kind of the recommended architecture for our Couchbase 4.0. In each node, you would have either the data service or a query service or an index service. Yes, if you want, you can mix and match. But to get the low latency and high throughput for your applications, we recommend you run one service in each node. And as I said earlier, installation and deployment and monitoring is all integrated, and it's very easy to go. So now let's drill down a little bit and see how the query service actually executes the query. If you know how SQL executes a query, SQL is executed in a traditional system. This is not so different from a traditional system. However, there are key differences I'll highlight as we move on. And the second thing to remember is each service can be on one or more nodes in a distributed cluster. That's the thing. Each component is typically on a single node in a traditional database system, whereas here, each node can be on multiple nodes and distributed across the cluster. OK, we get the query, a simple query from the client. Client sends this query across to the query service over the REST API. So all the client-server communication is over REST. It's a key detail to remember as we will revisit that later on. And once the query comes into the query service, we do the parsing, semantic check, and ensuring that the statement we get is semantically correct. We create a query plan. Right? Query plan, again, is similar to a flight plan that you create when you travel from one city to the other. We choose the right indexes. We choose the join orders. We do the join methods. And once the query plan is created, if this query happens to use any of the indexes available, this index can be on a GSI index that sits separately as a service, or it can be a view index that's co-located with the data services. We go ahead and use that index to filter out the documents that qualified for the query. And the index service returns a set of document keys. Remember, in Couchbase, for each document, you have a document key that lives outside of the document itself. So index service returns a set of document keys. And we go ahead and request the data service to send us the actual documents for those respective document keys. Once the documents are retrieved, we do the further join, aggregation, other filtering, and limit and offset processing within the query service before we send the results back to the application. the data that is stored within the data service is JSON. The data that is returned here is in JSON form, and the query is NIQL, right? It's a SQL++. And the last thing to note is the operations to request the index scan and retrieval of the qualified documents is running in parallel. So this is not, even though in animation showed as a serial service, as the document keys come back streaming in, we go ahead and get the data. If the query requires a large number of documents to be processed, all that is running in parallel. So that's the high-level overview of how the Couchbase query service executes. Let's go into details about how each of the phases execute. So it's important to understand how this phases execute so that when you design your application, when you design your indexes, when you're tuning your data modeling as well as the Couchbase services, knowing this distributed architecture helps you to optimize your system. You saw this picture from Gerald earlier. So we'll go through each of those phases in detail so you have a sense of how the query is executed within the Couchbase ecosystem. So we get the query from the client as usual. And the initial two phases, the parsing and planning, is a serial operation. For each query, there's a single thread that is executing, that is parsing the query, as well as doing the semantic check, followed by creation of the plan. Okay? Once we create the plan, for each query, there could be one or more indices that we use to evaluate the query. That's the index scan, followed by, so we request those index scans to be executed in parallel. That's what you see here, okay? And then that will be followed by fetch, joins, and so forth. So one thing to note here is when I have multiple arrows coming out of the operators, they're all running in parallel, essentially, right? So these two first phases ran serially. When you see multiple arrows, they're all running in parallel. Eventually, after the final aggregation is done, then again, we sort all the result set in parallel, if necessary, if you have order bys, followed by offset and limit. The second thing I want to highlight here is this is an execution pipeline for a simple SQL. SQL can be nested. You can have many levels of subqueries and many operators like union, intersect, except. So the phase between the scan and the project, this can itself be repeated over many queries. So this is a simplified form of the query plan. So if you have a sophisticated query that has many query blocks, they're all repeated. So that's important to remember. OK, so let's look at each of the phases of the query execution one by one. Okay? The client-server communication is always on REST, whether you're using the simple REST API or using Couchbase SDKs or a Simba driver. It's always REST-based protocol. That means you can use any of the open drivers that support REST on NIQL query service. Right? That's the beauty of it. The second thing is the query service itself is restless. Sorry, it uses REST, but it is stateless. If you're given it work, it is restless. It's always working continuously. Okay? It is stateless. That means you can spawn new query service at any time and submit the queries. You can switch between the queries services between multiple queries. If you have a application that and you are distributing the workload to multiple query services, you can issue a query to the query service 1 followed by query service 2. So you can switch over and do the load balancing very easily. And I mentioned this earlier. All our clients, whether it is NIQL clients, JDBC, ODBC, they all use REST. And at the bottom, I don't know if you guys at the back can see this clearly. At the bottom, I have given a 6-line code of this Python script connecting and executing a query and retrieving the results from the NIQL query service. I've worked in databases for like 25 years. This is one of the shortest, or if not the shortest, program I've seen to open a connection, execute a query, and get the results back. It really works. I've tested. OK, so now that we have the query from the application within the query service, first phase is to make sure syntactically the query is correct. Second thing we do is, if you have referenced any buckets, we ensure you have the buckets that you have referenced do exist. The third interesting thing is, since you don't define the schema, there are no missing columns or column not found errors in NIQL. Okay? So you have to be responsible. You have to verify that you are referencing the right attribute name. If you make a spelling mistake, we'll just project null. Okay? No column not found error, no type mismatch error. Right? So those are the two important attributes of a flexible data model. You have flexibility, but with that you get the responsibility of ensuring you have the right reference to the column names or the attribute names. So because the data model is flexible, you can have one document containing a zip code, other document does not contain a zip code. It has a postal code or something else. So we don't verify the schema on write. So when you're reading, if you project something that is not there, we'll project null. If you want to ensure, if you want to check if a certain attribute is present or not, you have to use the missing clause, so you know that returns true or false. Two other things. You saw the simple query earlier. It looks like SQL. It works like SQL. It talks like SQL, quacks like SQL. But we have extended the SQL to make sure you can address the JSON structure fully. That means two main things. You should be able to reach to any levels of hierarchy within the hierarchical JSON structure. So this is the dotted expression within the identifier allows you to do that. The second thing is, since you can have arrays, you can address the arrays with a square bracket, and you can mix and match. You can reference attribute values that are stored within arrays within hierarchical structures, so you can reach out to any levels or any hierarchical level within the JSON structure. Okay. And we have enhanced SQL to make sure you can not only access, you can manipulate, update, do all the operations on the complete JSON structure. Okay. So let's go through the phases. For people who know SQL, this is quite familiar. So the only difference is this query is being executed on the flexible data model. So the schema reference, everything is pretty dynamic. The reference to the JSON attribute name or the key name is exactly like how you reference a column within your SQL. In the projection clause, you can use any of the expressions that we support, all the arithmetic operations, logical operations, subqueries within the projection clause, all the standard things that you use in addition to the aggregate expressions within the projection clause. The bucket reference is just like a table reference. You can, when you want to join, you can have multiple bucket references. You can join the same bucket to itself as long as you have the primary key, foreign key relationships set up, or you don't explicitly set up the relationship, but you set up the keys in such a way that you reference the document key within the document that you're referencing. Predicates, again, this works just like SQL. If you are doing a predicate on a nested object, you just give, let's say, if you contacts.address.phone number, you can have a dotted reference anywhere within your query engine. And then you can order by any arbitrary complex expression within your query, followed by a top-end clause. That's the limit and the offset clause within our query engine. So now that we have a valid query, we have to create an execution plan. So each query can be executed in multiple ways, right? Usually. In SQL, you specify what needs to be done, not how it needs to be done, usually. And the planner or the optimizer within the query engine figures out how to execute this particular query and for this particular instance of the execution, right? So that means for each key space reference, when I say bucket reference, that means it's the key space. For each key space, we decide the access path, whether we are doing a primary index scan, secondary index scan, or a key scan. Then we decide which filters to push down, which filters that we have to retain, apply those filters after the documents are retrieved. Then decide on the join order and join method. In NIQL, right now, we always do the joins in exactly the order that you have specified in the query. Okay, that's the join order in this release right now. We don't change the order. And the join method that we use right now is the nested loop. So again, this is the behavior in the version 4.0 that we're going to release. And then once all these are decided, you create the execution tree, which the query engine executes. And then for each key reference, as I said earlier, we look at all the indices available for that particular key reference. And then we also group the filters available so that we can maximize pushing down the filters for the index scan. I mean, that's the whole idea of using the index, right? You want to maximize the performance of the query using the available indices. And once we select the indices, we group which part of the filters can be pushed down to the index and which filters cannot be pushed on the index because the filters is not on the leading n keys of the index, and then we apply the filters after that. And then, last but not the least, is for scanning each key space, we can use one or more indices for each key space. So we can do what is popularly known as the multi-index scan. Within the explain plan, you will see that as an index intersect or IntersectScan. That's basically a multi-index scan for the query processing. You have a question?
Typically in a relational database, when I give a query, one of the phases is an optimization phase.
Yes.
Where it looks at the heuristics, other possible indexes, and chooses the best plan based on that.
Yes.
I don't see that here. And
this is it. The planning phase is the optimization phase, right? When you say we plan, the purpose of the optimizer is to plan the query execution. This is the planner or the optimizer. This is what we have today is a rule-based optimizer. So we don't have the costing infrastructure. It's a distributed system with, you could have millions or billions of documents. asking you to run update statistics on the system is a little bit cruel, but eventually, statistics do help in creating the most optimal plan. So right now we have rule-based optimizer. Okay, so let's look at a simple query and get into the details of the plan. And one of the nice things in NIQL is the data model is based on JSON. The results are JSON, and even the explain plan you get in JSON. I worked in other databases before. The explain plan or the execution tree by nature is hierarchical, right? So to give it out in a flat structure is a little bit artificial, but the JSON structure lends very well into representing the query plan. Okay, so when you are looking at the explain plan, like I said, you give a query and prefix it with explain, you get the explain plan for the query. The focus, the part of the query plan to focus on is the index selection. What index are we choosing to execute this query? And then you have to see what filters are being pushed down. Those two are the important things, because remember, join order, join method is fixed. Right now, when you look at the explain plan, look at the index that is selected as well as the predicate that is pushed down. Last thing on this slide is you can get explain not only for select statement, you can get explain for any of the update delete statement as well. So you know which index is being used to target the subset of the documents to delete. So that's one of the nice things. Insert has only one plan, by the way. Okay. So for the query we saw, we have 3 predicates. One on warehouse ID, district ID, and last name. Okay. For that set of predicates, we have a matching index that chooses all the 3, that pushes down all the 3 filters. So that's the best fit, right? So if you can push down all the filters, then you get the maximum performance. So the key thing is look at the index that is chosen and look at the index, the operator type, whether it is a primary scan, key scan, or an index scan. If you have created secondary indices, when we choose that, it's always index scan. There could be intersect scan on top of this or a union scan on top of this, but the core operator is index scan. And then we have filters pushed down. And we'll look into the intersect scan later on, but the key thing is in the scan phase, we could be requesting multiple indices. If you have chosen multiple indices, we could be requesting multiple indices to do the scan and return the result sets for us. Okay? Once the index scan is done, we go ahead and fetch the data from the data service in parallel. And I want to highlight one thing here. The indices in Couchbase is maintained asynchronously. That means the data in the index is slightly behind the actual data within the data nodes, right? And we want to make sure the results you get will not have any data that does not qualify your filters. So what we do is, after we get the set of document keys from your index, we get the data, we get those documents from the data service, then we reapply the filters to make sure you don't get any wrong results. Right? Because things are asynchronously maintained, even in few milliseconds, there could be thousands of inserts, updates that can potentially get you some results that you don't expect. So we reapply the filter. So that means the results you get are always guaranteed to qualify for the filters that you are given. You have a question?
Is there any scenario where, even though the index is there, but the optimizer or the execution plan will opt for a full scan?
Yeah. The question is there any scenario that even if there is an index, you still choose the full scan. If you have a qualifying filter, the first n keys to the index are used in the query, we will use the index always, right? So here again, we don't have statistics, right? If the filter qualifies for 80% of your range, we still go ahead and choose the index because we don't know the statistics of it right now, right? If we have statistics, then we can say, hey, primary scan is faster than this. But right now, if you have a qualifying filter, we always choose the index. Yeah, finally, after the filter processing is done, did I skip over? Processing is done, we go through the projection and project it out. So this is basically the overview of the plan. We go through the rest of the phases as well. Okay? So now we are revisiting the scanning phase. In the scanning phase, like I said earlier, we have 3 options. We can either use the view indexes or the GSI indexes. So we are agnostic to what types of indexes that you create. Obviously, each type of index has a performance impact, right? So Jihan talked about the advantages of GSI index. John Leong is going to talk in detail about the architecture, implementation, advantages of global secondary indexes following this talk. But from a query service point of view, whatever qualifying indexes that you have, we pick up that particular index and then execute it. So once we request the indexes for filtering out the data and give us the results back, and if multiple indices qualify, whether it is multiple GSI indices or multiple view indexes, we go ahead and request those respective indices to do the index scan and give us the results. Once the qualifying document keys are back, we go through the cluster map, just like a key value lookup that you're used to seeing in Couchbase, and do the data fetch on the data service. I will revisit key scan later on, so I'll pass this for now. So when we get the document keys from the index, we batch them together and request the documents to be sent to us in batches. So we optimize the size of the batch depending on the size of the result set. And yeah, when you have use keys, we request for the particular documents directly from the data service. So we'll, again, revisit that in a few minutes. Fetch requests are done in parallel, and join operations use the fetch operation to get the matching document. So when you're joining from one table to the other, you're always joining from the target table lookup is always on the document key. And the document key lookup is always through the key scan. Okay? Only when you're joining multiple tables, whether you're joining 2 tables or 20 tables, index selection happens only on the leading key space of the join. Rest of the tables are accessed through the key scan method. That means we get the document key and we directly go through the cluster map. In this release, that's the execution plan. And document key is the fastest way to get to the data anyway. And for larger queries, for complex queries which are doing reporting, aggregation, trend analysis, a lot of these phases, scans, fetch, join filters can be happening in parallel. Yeah. Next comes the join. You can join any 2 key spaces if one has a reference to the document key of the other key space. You cannot join any random attribute names between 2 key spaces. One has to reference a document key of the other key space. The second question is, do I have to have the complete document key in a single attribute name? The answer is no. If you have a document key that is composed of customer ID, zip ID, status, you can have those 3 values in separate attribute names. During the join, you can concatenate those things within your join clause. So you don't have to have it in a single attribute name, but if it's there, it's just easy for your query. From the execution point of view, there is no change at all. We use nested loop joins right now. Again, this is the 1.0 release, and joins are done in the same order as before. Yeah, and index selection happens for the first key space, whether you give 1 key space or multiple key spaces. So rest of the keys are joined using the document key. Let's look at an example. I have customer document with a customer document key, and each customer can have multiple orders. And in this case, I happen to have the customer keys stored as a separate field within this document. You could have this 1, 10, and 1938 stored separately as well. You can combine them at runtime. And that has a reference not to some field here. It has to reference the document key that you have specified during insert. Again, same thing. This particular reference that sits inside the document has to reference the document key that sits outside of the document as a document key in the Couchbase key value. So that it's an important thing to remember. I moved from relational databases to this world. I learned my lesson, so I just want to make sure my friends know this as well. And we support 2 types of joins, inner join and left outer join. This is an example of an inner join. That means we join orders. I want to find out total number of orders pending for this filter. Okay? I'm joining orders with customer with O customer key as the join clause. That means this O customer key from O is joined with the document key of the customer. Okay? So you can cascade these joins. You can mix and match between the inner join and left outer join. But remember, you join always with the keys, and joins are executed in the same order. Any questions on joins? All of you are experts on joins in NIQL right now. There'll be a quiz following this.
What's the premium clause?
No, left join premium is another key space. Okay. Next phase for us is filters. So obviously, we want to push down as many filters as possible. Following the IntersectScan, any remaining filters will be applied by the NIQL query engine. Following that is the standard aggregation order by and offset limit. So this is kind of a standard thing. Within each result set, as I said, result set in Couchbase or NIQL gets the results in JSON. You get a describe. It describes what the results you get. See here, in this case, czip, it is described as JSON because we have no idea what is the type of this particular attribute name. When we don't know, we say JSON. When we do know, in this case, count star has to be a number, we say it's a number. And this is the sample result set. And finally, we have some metadata on what was the elapsed time, what was the execution time on this. Okay, we went through this already. Okay, now quickly, in another 10 minutes, I'll go through some of the power features that I mentioned. And Q&A will be after the session. Like I said, there'll be a break. I'll be around if you have any questions. So you have seen the access methods to the data, index access method as well as the key scan. And what I'm going to show you is how the key scan works. This is how we are bringing NoSQL into SQL. If you use keys as a modifier to the key space clause, that means for the use keys clause, you can give one or more document keys as arguments. This is an array, and for all the document keys, we go directly to the key scan. Right? We don't use any indexes. We go directly through we reference the cluster map and get to the document directly. This is the fastest way to get to the data within Couchbase. When you want to access this keys directly from SQL, you can do a meta of this customer. In this case, customer is the key space, and .id will give you the key space. And here, for a query like this, here is an example where I have used multiple keys, and you use the explain will give you the key scan. One of the advantages is once you get the document back, you can do further processing within NIQL without having to write any complex program. That's the beauty of it. You can not only use keys for select, you can use keys for update and deletes as well. So again, rest of the SQL doesn't change. When you use keys, your access to the data becomes much quicker. Inserts, you always have to specify the keys. There's a key expression. There's no use keys there. Merge, there's a use keys, so I won't go into merge in this talk. Okay, you heard about nesting and unnesting. I'm going to show a simple example of unnesting here. So I have a denormalized customer document where I have embedded all the orders and order lines within a single customer document. Sometimes when you have to denormalize, you denormalize, right? So if you have denormalized, how can you access the data embedded within the arrays? There is a top-level JSON structure that has got an array called orders. Array itself is an array of structures, array of substructures, which itself is an array. Okay. You don't have to write any complex program. This is as simple as this. You take customer, orders is an array under customer. You simply unnest. It just becomes flattened. And you say, how am I going to reference these orders? You give it a name, my orders. Once you give my orders, you can use my orders as a standard key space anywhere in the query. Then my orders has some basic elements, but it also has another array called order line. Again, you can unnest the order line and simply reference those things as well. So navigating a complex JSON structure within NIQL is as easy as SQL. Question there?
So for those things that don't have orders, it's treated as something like a left outer join?
Yeah, if it doesn't have orders, that's exactly right. So there is nothing to join, so you get the same document there, yes. Yeah, there is nothing, it is a left outer join. Because the left side has to be retained, right? So that's how the projection is done. Any other question on unnest? Okay. So we saw the phases of query execution earlier. So in databases, we use a trick. There are two things. One is, you remember the parse and the plan is a single-threaded execution. And for queries that are running in milliseconds or microseconds, the overhead of parsing and planning the query is expensive, right? So you want to prepare the query once and bind multiple values. This is a standard technique that's used in RDBMS programs forever. So we support that as well. So you can prepare your statement once, and this, you just prefix the state. Again, this is another Python script. You prefix your statement with a prepare keyword, and you get an ID for the prepared word. And then when you submit the query, you simply say prepared equals this prepared statement ID that you return, and then you simply keep binding different values. Okay, so that's and you will save on the prepared on this prepared time for how many ever times that you execute this query. So we have seen significant improvement, latency improvements, anywhere from 10% to 30%, depending on the complexity of a query. If your query is running for 10 minutes, yeah, savings is not much. If your query is running for 2 milliseconds, 5 million times a day, savings are significant. Okay. Prepare once, bind many times, bind and execute many times. That's the model. We have very flexible indexing creation as well as selection mechanism. So you can not only create indexes on directly on the attribute name anywhere in the JSON document. You can also use expressions within the keys, and you can also have expressions outside of the keys to divide the index. I'm just going to show the examples of where you can create so-called the functional indices. Instead of creating the index on the attribute name directly, you're creating the index on the expression here. For example, it's very common when you want to search by name, you want to search by case insensitive, in a case insensitive way. Here, I'm simply lowering, basically getting the lowercase value of the last name. So once I create this index, whenever you issue a query on lower of this L name, we'll choose the index. We'll choose the index IDX L lower. So that the expression here in the where clause, lower of L name, has to match the expression here in the functional index. That's the key. Okay? So always use explain to verify that your query is using the right explain plan. Okay? Multi-indexes. So you have seen the examples of composite indexes earlier. So you can create composite indexes with anywhere from 1 to 4,000 keys. The first n values have to be, n keys have to be matched in the predicate for us to choose the index. But there are situations where when you have many combinations of composite indexes, number of composite indexes can become high. Index maintenance, index storage, the overhead can become quite high. So what we have done is, if you have indexes or multiple indexes on multiple filters of the query, we can choose multiple indices to evaluate a single query. That's what we call the index intersect. And this can save both the disk space, memory, and since if the indices live on distinct nodes, again, these things get parallelized. Even if the indices live on the same node, because these two are different indices, the scans on those indices are happening in parallel. Okay? This is a explain plan showing for this query, we have chosen the index intersect, and you can see we have chosen 2 different indices. One is on the city, one is on the last name. We request for these scans in parallel. Once we get the results back, we basically do the intersection of it. One of the interesting aspects of this is if one of the, if in this case it's an AND clause, if one of the scans complete faster than the other, we can simply abort the other scan and speed up the query as well. So this, in one single case, it compensates for the lack of actual statistics within the system. Exactly 45 minutes. I'm at the end of the talk. So we have, you can visit query.couchbase.com, download the beta, play around with our tutorial. We have plenty of information there. So I'm here to answer any questions. Thank you for attending.